All right, let's get right into it. We are going to pull back the curtain on the one piece of technology that's behind pretty much every single major AI breakthrough you've heard about lately. I'm talking ChatGPT, Gemini, you name it. We're talking about the transformer architecture. This is the engine of modern AI.
Okay, so let's kick things off with a pretty bad joke. Why did the banana cross the road? Because it was sick of being mashed. Now look, it's not winning any comedy awards, I get it, but what's really fascinating here isn't the punchline.
It's who, or I guess what, told it. An AI based on a transformer came up with that. And that just begs the question, right? How on earth does a machine learn the structure of a joke, or get the wordplay, and then create something that's actually, coherent? Well, that's exactly what we're about to unpack.
To really get why the Transformer was such a revolution, we have to hop in a time machine and go back to the days before 2017. Back then, AI had a huge problem with language. It basically had a terrible, terrible memory.
See, the old way of doing things, with models called recurrent neural networks, or RNNs, was to process language one word at a time. Seriously, just picture a long conveyor belt. The model sees the word the, then quick, then brown, and so on, down the line.
And this whole conveyor belt thing, it created this massive bottleneck called the vanishing gradient problem. What that really means is that by the time the model got to the end of a long sentence or a paragraph, the important context from the beginning was, well, it was basically gone. It just forgot.
And it wasn't just about memory, it was a speed issue too. This old method was painfully slow. Because every single word had to be processed in order, you couldn't really train the models in parallel. So there was this hard limit, a real ceiling on what AI could ever hope to understand.
And then 2017 happened. A single research paper from Google came out and just completely flipped the script. And the title? Attention is all you need.
What a title, right? It's this clever nod to the Beatles, sure, but it was also making this incredibly bold statement. The paper introduced the transformer, and it basically argued that all that complicated one-word-at-a-time processing wasn't just unnecessary, it was the actual problem.
So the transformer just tossed out the conveyor belt entirely. And in its place, it used something more like a satellite map. So instead of looking at one word at a time, it sees the entire sentence, even a whole document, all at once, instantly. Every word has a direct line to every other word.
And this new way just blew the old problems out of the water. When you process all the words at once, the full context is always right there. But here's the real kicker. The training could be massively parallelized. And that meant we could throw just enormous amounts of computer power at the problem, which, as you'll see, unlocked everything that came next.
Okay, so hold on. This brings up a pretty big question. If the model isn't reading word by word anymore, how in the world does it understand context? How does it even know which word came before another?
Let's use an example. Take the word server. How can a model possibly know that this one word can mean two totally different things? It all comes down to the words around it, right? In that first sentence, the word check is the big clue. In the second one, it's the word crashed. You and I, we get this instantly. But how do you teach a machine to do that when it's looking at everything at the same time? Well, the secret sauce, the magic ingredient, is a mechanism called self-attention. This is what lets the model, for any word it's looking at, figure out the importance of all the other words in the sentence. It literally learns which words provide the most context and deserve more attention.
A really cool way to think about this is like searching on YouTube. The word the model's focused on, say server, that's your query. All the other words in the sentence are like videos, and they each have keys that say what they're about. The model then scores how well your query matches each key, and the words with the highest scores, like crashed or check, they get the most attention. Simple as that.
So that handles context, but what about word order? Without it, a transformer would see the dog bit the man and the man bit the dog as exactly the same thing. To fix this, the researchers came up with this really clever trick called positional encoding. It's basically a unique mathematical timestamp that gets attached to each word, giving the model a sense of order without having to go one by one.
Okay, so this new architecture was way faster, way smarter. But its biggest impact, the thing that changed everything, was that it allowed AI models to get, well, unimaginably bigger. And this is what we call the billion-parameter leap.
Just take a second and look at that number, 175 billion.
That is the number of parameters in the GPT-3 model. You can think of parameters as these little tunable knobs that the model adjusts while it's learning. Before transformers, the biggest models had maybe a few million knobs.
The parallel design of the transformer is what made this insane jump from millions to billions even possible.
And this incredible scale is what changed the game. Suddenly, you had amazing hardware efficiency. You could train on these massive datasets, I mean literally chunks of the entire internet. The architecture is also super versatile. But then, something else started to happen. Something kind of weird and almost magical. And this leads us to the most mind-bending and maybe the most mysterious consequence of the transformer architecture, this phenomenon called emergence.
Emergence is what happens when a model, just by getting bigger and bigger, starts developing complex skills it was never ever taught. Remember, a model is only trained to do one thing, predict the next word. But researchers found that to get really, really good at predicting the next word in, say, a math problem, the model first had to figure out how to do math. These skills just emerged. They woke up.
And that leaves us with this huge, profound question. If just making these models bigger unlocks abilities that we never programmed into them, what new skills are just waiting around the corner to emerge? That is the powerful and kind of wild reality we're building right now, one layer of self-attention at a time.